All right. So, as I said, I will focus mainly on antenna and RF component design. So this year, along with CST, we have many different additional synthesis tools like antenna makers, WaspNet, etc. And we try to unify the installation process. So if you install latest CST Studio Suite 2025, the antenna makers will also get installed. So if you have the license, you can already start using the makers. But even if you don't have the antenna makers license, you can still use the antennas from the makers because we now provide almost 30 different antenna designs from antenna makers directly in the CST component library. Those designs are frequency scalable, meaning you can tune each of those antennas to your desired frequency, and all the parameters will be set accordingly. Couple of years ago, we have an acquisition called WaspNet, which is mainly meant for waveguide and antenna synthesis. That's also got unified with the installation, and you can use the tool if you have our unified or if you are on our unified licensing scheme. All right. For unit cell analysis, usually you define a unit cell geometry and define the unit cell boundary conditions. And this would require a frequency domain solver to be used to solve. But now you can also use time domain solver because time domain solver also got this blockade unit cell simulation functionality that enables the simulation of very large, electrically large unit cell, especially useful in optical domains. But not only that, you could also utilize the GPU acceleration to speed up the simulation. For reflect array and large metasurfaces, we now have the synthesis in antenna makers. Once you synthesize these kind of reflect arrays, in order to solve it, we now have a new solver available through WaspNet, and we now allow you to export the synthesis of metasurfaces or reflect arrays from antenna makers to WaspNet. As an example, I have a reflect array of this kind of Minkowski unit cell, which typically takes hours of simulation time in MLFMM solver or FEM solver. But in advanced adaptive integral method in WaspNet, it took only 16 minutes per frequency, as indicated here. You could see the simulation results like gain and cross polarization also plotted. Not only that, the tool also comes with advanced solvers like body of revolution and iterative physical optic methods, which will enable you to solve very quickly this kind of complex corrugated phone with lens and complex feed networks quite quickly. So these kind of feed networks are typically used for subreflectors and main reflectors. And as an example, this kind of Gregorian reflector system. And we are talking about solving this kind of entire system, antenna reflector system, solving this in terms of few seconds. You can see that you could also accelerate the simulation using GPU. It could considerably reduce the simulation time. Keep in mind that this simulation time of 18 seconds or 12 seconds is for one frequency point. So for broadband simulation, definitely you need to solve multiple frequency points. Nevertheless, compared to a full base solver, this is a huge speed up utilizing these kind of specialized solvers. There are more enhancements in WaspNet. The tool also now supports dielectric loaded or surface integrated waveguide kind of slotted waveguide arrays. This kind of complex array synthesis is now easily possible with the tool. Not only that, as part of the integration process, WaspNet results, especially the far field results, can be directly accessed by exporting to CST Studio Suite. So that you can now available this far field generated through the simulation from WaspNet for advanced post-processing. In frequency domain method, we introduced the so-called domain decomposition method a few years ago, which is very beneficial to solve electrically large and complex arrays. As an example, I have a base station array here, which is electrically large, consisting of almost 68 ports for high band elements operating in sub-6 gigahertz 5G frequency. This is being solved in around 3.5 hours in latest software version, which is not possible with the classical finite element method or the previous versions of the software, right? But not only that, you can also utilize GPU acceleration for domain decomposition method. Of course, you can also send this particular model to multi-node MPI technique, which also being supported by the domain decomposition method. We always try to support the latest and greatest GPUs which are being released. As part of the process, you could now see that the CST's most sought after solvers like time domain FIT solver and particle in cell solvers are being accelerated with the latest GPUs, including A100s and H100s. You can see the speed up is almost 50 to 20 times compared to a standard workstation, which doesn't have a GPU, which is the baseline. Not only the solver, we try to integrate or accelerate all parts of the simulation process in GPU. And with that, now you could also accelerate the SAR calculation. The SAR calculation for body model used to take significant amount of time if you have full body model. That can also now be accelerated using GPU, which reduces the simulation time significantly. As a summary, we try to support all the solvers in CST through GPU. With that, now frequency domain solver, especially the domain decomposition solver, now supports GPU and MPI computing. This is in the preview stage though, but it's already available with the software. Last year, again, we expanded the portfolio, enabling you to do the system simulation, not only the 3D electromagnetic simulation of the antenna or antenna arrays, but now you can also include the power amplifier, for instance, to do a system simulation of the communication, entire communication model. With that, you can see the effect of power amplifier, like intermodulation or unwanted operation scenario with the power amplifier on the performance of the antenna. After the system simulation, all the relevant results will be available in a whiteboard, which is very dynamic and interactive dashboard, on which you could get to see different results, including the far field of the antenna. You could compare the isolated far field when you do the antenna simulation standalone, compared against when you are connected with the active elements like power amplifier. You can see some degradation in the performance when you include the system along with the antenna arrays. In summary, you typically start with an element design and you proceed to design the full array elements, and we provide a standard workflow for this. But along with that, now we could also be using the software for doing the system simulation. For waveguide synthesis, for example, filters, couplers, and dividers, we used to provide, or we provide a software called FIS3D. Now, from FIS3D, models can be exported to Microwave Studio, including the model parameters. What that means is, once exported, you will be able to edit the individual waveguide parameters in CST if you want to modify the synthesized model. Spark3D is a tool for analyzing the breakdown like multiplication and corona discharge. And in the latest version, we try to add more and more material property, and this now supports the ECSS 2020 European multi-factor standard. So that is again improvement in this particular area. So in summary, for microwave component design, especially the filter design, you typically start with the specification. For example, if you want to design a bandpass filter, you start off specifying the passband stopband criteria, and the software will give you certain topology by which you can synthesize it. Once you select a topology, software can also suggest you typical components by which you can synthesize the model. And once you choose each component, again, the software automatically sets up an optimizer, optimizing each individual component and assemble it all together automatically and do the final analysis, including the optimization. You could also connect the software to the hardware so that you can do real-time tuning through the feedback obtained from the filter designer 3D software. right? So the software will help you to tell you which exact tuning screw needs to be adjusted to achieve the performance when you do the hardware in loop tuning. Right. We also provide, apart from standard optimizer built-in, we also now have a non-parametric optimization. What that means is you don't need a variable for your 3D model to do the optimization. Like for example, you can see a horn antenna with its feeding network, the diplexer, complex cavity filters also associated. We used non-parametric optimizer to optimize each component individually, including the horn antenna, the septum polarizer, as well as the cavity filters. You could see that the complex shape of this antenna and feed system is achieved through non-parametric optimization. So in summary, we improved not only all the solver technologies, but we also expanded the portfolio to antenna system simulation, synthesis tools, etc. Now you can see more automated workflows available for antenna arrays and the solver enhancements in domain decompositions, PLM solver, etc. You can now do system simulation with MCAD Vision software, which is now part of the CST portfolio. And we also integrated or unified the installation so that all the tools, including Megas, WaspNet, etc., along with CST, will be installed in one package. New solver capabilities and improvements for reflect arrays, which we talked about, and also filter design automation in FS3D, FT3D, etc. And finally, non-parametric optimization for antenna and component devices is also not now possible with the Tosca technology.